So in ripple carry adder, so the every full order cell has to wait for the incoming carry before an outgoing carry has to be generated. So one way to get around this is linear dependency is to anticipate both possible value of the carry input and evaluate the result of the both possibility in advance. Once there is real value of the incoming carry is known, the correct result is easily selected with the help of simple mux stages. So the implement of this idea is called as carry select adder. So consider the block of adder. So here I have added 8 ones with the 1 000 1 000. So this I have split into A0 to A3 and A4 to A7. So here if you see this point that is A3 value. So in the A3 I have generated the carry as 1. So previously I have calculated the values for in the left hand side you see what will be the answer if the since the from the C3 value I have uh, the carry value is 1, I have already calculated that value. So if it is 0 also I have already calculated the value. So this will be given to a mux stage. So based on this carry C3 value I have select either the two values, right? So this is a carry select added for the 12-bit data. So here also you can see from the 4-bit the C3 value, okay, the C here it is mentioned as C. So I have calculated the value of C7 and C7 values if the C3 values 0 or 1. So if you see the critical path delay, 4T carry is a delay for the first 4 full adders in the right hand side, and for the second block you have 4T carry plus a mux, okay, and for the third block also you have 4T carry plus T mux, that is these one, okay, these and this one. So I can write it as T critical is equal to 12T carry plus 2 T mux. So for 16-bit data, it is nothing but 16 T carry plus 3 T mux. So I can write T critical is equal to N T carry plus N by K minus 1 into T mux. So here N represent if it is 16, K represent 4. Okay, so 16 divided by 4 is minus 1. You will get 3 into T mux. Okay. So let us now discuss about the linear carry select adder. So the red line represent the critical path. So if you see, you can see you have a T setup and either 0 carry or 1 carry will be selected. So for that one you require M into T carry, and here M represent 4-bit, and totally I have this is nothing but a 16-bit adder. So I have split it into 4 bits. So N is equal to 4-bit. So you can see I have used 4 muxes. So I can write it as N by M into T mux, okay, plus T sum if the if I want to calculate the critical path for the sum. So here I can set the T setup, T sum, T mux as a fixed delay that is equal to 2 nanosecond, and N is nothing but a total number of bits, that is 16-bit, and M is equal to total number of bits per stage, that is 4 bits, and T carry is equal to delay of the carry through a single full adder cell. Here the propagation delay of the adder, that is T critical, is linearly proportional to N. So you can see the equation. So that is why it is called as linear carry select adder. So the reason for the linear behavior is that the block select signal that selects between 0 and 1 solutions, still it has to ripple through all the stage in the worst case. Let us now discuss about the carry root, square root carry select adder. So in order to optimize the above circuit, we have to consider to reduce the critical timing path first. So for that, let us take that 16-bit linear carry select adder. Assume the full adder and the mux cell has an identical propagation delay equal to a normalized value to 1. So this is a block diagram of square root carry select adder for 11-bit adder. Okay. So here I have selected the first 2-bit. Okay, and next one also 2-bit. That is A0 to A1 first and A2 to A3. Next, I'm going to add one more bit. Okay, so first block is 2, second block also 2, third block is 3, fourth block is 4, and it will go on. So I can write n is equal to k plus k plus k plus 1 plus k plus 2. So if the n value is 11-bit, so k is equal to 2, you can substitute the formula, you will get the answer LHS equal to RHS. So if it is 16, means n is equal to k plus up to k plus 3. So I can write n is equal to k plus 1 up to k plus p minus 2, where p is the last block bit. So here, since it is 11-bit adder, for here the p value is the last bit, that is equal to 4 for the 11-bit adder. Okay, so I can write this formula, n is equal to pk plus 1 plus 2 plus p minus 2. Here the k value is equal to 2 and the p value is equal to 4. So I can write 11 is equal to 4 into 2 plus 1 plus 2, that is equal to 11. So LHS is equal to RHS. So we know that 1 plus 2 plus up to p is equal to p into p plus 1 divided by 2. So here it is written as 1 plus 2 plus up to p minus 2. So instead of p, I am going to substitute p minus 2 into p minus 1 divided by 2. So you substitute in this formula. So n is equal to pk plus p minus 2 into p minus 1 divided by 2. Since p value is greater than k and p value is greater than 2, you can write n is equal to pk plus p square divided by 2. And since p value is greater than k, I can further reduce the values. So that n is equal to p square by 2. From this, I can write p is equal to root of 2n. So since the value of n is equal to 11, if you substitute in the value of p, so you will get p is equal to 4.69. I approximated it to 4. So my critical path, T critical is equal to T sum plus n T carry plus root of 2n minus 1 into T sum, T max. So if you substitute, you will get T sum plus n T carry is 11 T carry plus 3 T max is required. So if you compare means for larger value of n, the T critical value is about constant. Okay, so for smaller values of n, the T critical values is same compared to the ripple carry adder and carry look adder. But if we go for the larger values, the T critical values very less. So this is the advantage of carry select adder.